Hi, my name is Joan Brennecke, and I'm the Keating Crawford Professor in the Department of Chemical and Biomolecular Engineering at the University of Notre Dame. My research interests are really in developing more environmentally friendly solvents for a wide variety of industrial processes. We did a lot of work with supercritical CO2, and now we've been really focusing on ionic liquids. And ionic liquids are simply salts that have low melting points. And most of these will actually be liquids at room temperature. And the reason why they're attractive from an environmental point of view is that because they're salts, they have strong coulombic forces, and that means they don't like to evaporate, so they have incredibly low vapor pressures. So this means that if we use them as solvents in processes, we wouldn't have to worry about fugitive emissions into the atmosphere. So we really eliminate the whole atmospheric pollution problem. We of course still have to worry about if they get into wastewater, but at least we've eliminated one of the potential ways that these solvents could impact the environment. We've been particularly looking at using ionic liquids for doing gas separations. And one of the big gas separations that we care about is removing carbon dioxide from post-combustion flue gas, because we still use about 85% of our primary energy comes from fossil fuels, and of course burning those fossil fuels has contributed to the increase in carbon dioxide concentrations in the atmosphere. And so we look at point sources like power plants as a good place to try to remove that CO2 and use it for other purposes, enhanced oil recovery or geological sequestration. Problem is that current technologies would require a very large amount of the energy from the power plant to run the separation process, almost maybe 30% of that energy. And so we would like to be able to develop materials who could do the separation with much lower energy burden. The best materials that we've been able to find actually are ones that are in fact solid at operating conditions. Our favorite one has a melting point of 166 centigrade, but when it reacts, and it actually reacts with CO2 because we have an amine functionality in the anion of the ionic liquid. When it reacts with the CO2, that new complex has a much lower melting point. And that means that in the regeneration process, where we would take that liquid complex and remove the CO2, usually this has to be done by adding a lot of heat because you're trying to overcome the delta H of reaction. But now part of our heat is provided by that liquid. When it releases the CO2, goes back to a solid. So the amount of heat that we have to add in the regeneration process is significantly reduced. And we've done all of the fundamental work and had some colleagues at a company called Matrix who did the process modeling, and it looks like this process would require only about 23% of the energy of the power plant instead of 28 or 30% from the aqueous amines from the current technology. And while that may not sound like a really big improvement, in fact is, because the thermodynamic minimum is about 15%. So that's the very, very best you could do if you didn't have any irreversibilities in the process. So we're very excited about this result. Discovering the materials was actually by accident. We made a material that was a solid at room temperature, and my student was disappointed that it wasn't an ionic liquid at room, it wasn't a liquid at room temperature, but I told him to go ahead and measure the CO2 uptake at a higher temperature, and he did that. And then he turned the heater off, but left 1 bar of CO2 pressure on the apparatus, and when he came back in the morning, in the flask, it was still a liquid, and he had expected that it would have turned back to a solid. And so that was sort of the serendipitous discovery that led us to develop these materials. Other things that I'm interested in doing is developing ionic liquids for other gas separations. We've really been focusing on this post-combustion flue gas, but certainly there's many other CO2 separations that are important. Industrially, removing CO2 from natural gas is incredibly important, and we really haven't just gotten around to optimizing ionic liquids for that particular application. I'm also very interested in using ionic liquids as electrolytes. The key to this is to have ones that not just have relatively lower viscosities, but ones that actually can conduct your ions or conduct the species that you want. And we have some indication that some of the ionic liquids that we actually have developed for the CO2 capture application may in fact be better for things like lithium-ion batteries, that the conductivity of the lithium is not slowed down the way it is in some of the other ionic liquids that people have developed. So those are some of the things that we're interested in pursuing in the future.